And there we go, 12. Got your results here. That's from my little extension of the spring. I've written it up nicely for you. Feel free to pause at this point and actually copy it down. Drawn the graph, and I've got extension along the bottom in meters. Remember, extension is how far the spring extends. It doesn't actually have anything to do with the length of the spring. A lot of experimental results have the length of the spring, and then they have the length of the extended spring. You have to calculate the extension because it's how much it stretches. It's a straight line. Yay! Easy. What does that mean? It means that force is proportional to extension. F is proportional to x. We can calculate the gradient of it. Look. M equals rise over run 4 over 0.03. M equals 133. Easy. You're going to be more accurate than that, so if it doesn't work out the same as mine, it's because you've got proper graph paper. The equation then is F equals 133x. What else can we say? Well, you can compare it to Hooke's law in your book, which says F equals kx, which means that k for our spring is 133. That's called the spring constant. I'll write it here. Now, what does that mean? Well, it's a value that tells you that how far the spring will stretch depending on how much force you apply to it. It also works for compressing springs as well. It only works for springs which follow Hooke's law. If you go beyond what's called the elastic limit, it is no longer a nice straight line like this, and your string is broken. It means it will not return to its original value. It will not return to its original length. You have gone beyond the elastic limit. What are the units of K? Let's find out. Blue pen. Rearrange that equation there, and you will get K equals F over X. That's reasonable because it's the rise there over the run there. If you put the units in, you get newtons divided by meters, which means the units for K must be newtons per meter. So we can put newtons per meter there as the units. Or you have newtons meter there. Alright? Now, that wasn't particularly difficult, was it? And this is pretty well the end of mechanics unit. What else can you say? You can say that big heavy springs will require more newtons to pull it 1 meter. So 133 is for a reasonably light spring. If you've got something like a trampoline spring, it's going to be a much larger number. If you've got like a spring in a car, it will be a smaller number than a suspension spring in a ute or even a large truck. So next, once we've finished all this, since you're listening, we are going to do a practice exam paper. Don't get too stressed about that. And then we are going to write a report on mechanics. Alright? Thanks for listening.